So the effective value for a periodic waveform is a mathematical construct that electrical engineers use really in order to not have to carry around a bunch of unnecessary information. So let me explain what I mean by that slightly pictorially here. I'm going to try to draw something. It's going to be bad because I'm bad at drawing, but please bear with me. So what I am attempting to draw here is a receptacle that you might see here in the United States, which supplies electricity to electrical devices like toasters, computers, and all that kind of good stuff. There's typically a small slot like this, a large slot like this, and then a semicircular slot like this. The semicircular slot at the bottom is where our ground connection is made. And we have over here what we are going to call our neutral wire. And on the right-hand side, we have what's commonly referred to as a hot wire. And there is a potential difference between the hot wire and the neutral wire. So for a receptacle here in the United States, can anybody tell me what that potential difference is? It's not 5 volts. Anybody else got a guess? So what I'm asking you for is what voltage is supplied by an outlet here in the US? All right, nobody's volunteering anything, so I will tell you. This is commonly referred to as 120 volts. Have any of you guys ever heard of that? Okay, I'm very surprised actually. All right, so then my way of approaching effective values is going to be obtuse because I'm used to having people that are familiar with the fact that an outlet gives us 120 volts. So the 120 volts that's given to us by an outlet isn't actually 120 volts. So let me explain what I mean by that. Here in the United States, electricity is distributed using AC signals or sinusoidal voltages, okay? The 120 volts that I have listed right here is actually what's called the effective value for the following voltage waveform. V of t is equal to 169.706 cosine 120 pi t plus some phase angle theta v that depends on really when we start making our measurement. Now, as you might have noticed, especially in yesterday's lecture, carrying around this whole large representation of voltage gets very cumbersome, and it makes power calculations kind of difficult, which we saw yesterday. So instead, electrical engineers developed the concept of an effective value. So what an effective value is this, okay? An effective value is an equivalent DC signal which delivers the same amount of average power as a periodic signal. So if we had a resistor, the average power delivered to a resistor in a DC circuit is simply the DC voltage drop across the resistor squared divided by the resistor value. For a periodic signal, the average value of the absorbed power would be 1 over T times the integral over 1 period of the voltage squared divided by the resistor value by dt. This is just using our average value of a periodic signal relationship that we developed at the end of our last class. Well, the effective value is just the DC value that gives us the same amount of average power as our periodic signal. So we're going to derive an equation here. It's only going to take a step or two to get the effective value for a periodic voltage, okay? I'm going to do this by equating these two relationships for average power. So we can see that VDC squared over R will be equal to 1 over T times the integral over 1 period of V of T, our periodic voltage waveform, squared divided by R, and then multiplied by dt. Now, there is a factor of 1 over R on both sides of our equation, so they cancel each other out. From that, if my stylus will write, we have the relationship that VDC squared is equal to 1 over T integral from 0 to T of our periodic voltage waveform squared multiplied by dt. And since we're trying to find the equivalent DC signal, we'll simply take the square root of both sides. So the equivalent DC signal, VDC, becomes the square root of 1 over T times the integral from 0 to T of V of T squared dt. So this DC number delivers the exact same amount of average power as our voltage, a periodic voltage waveform V of t. I will call this V effective at times, literally meaning the effective value of the voltage. And I may also call it VRMS, where the subscript RMS stands for root mean squared. And we use this 3-letter subscript here because it tells us what math we're doing in order to get the effective value. We are taking the square root of the arithmetic mean or average of the square of our periodic waveform. We could follow a very similar derivation for currents. And what we would find is that IDC will be the square root of 1 over the period times the integral over 1 period of the square of our periodic current waveform by dt. And we might call this I effective or IRMS. Now, typically speaking, we should use the units of volts RMS or amps RMS to distinguish between true DC signals and the effective value for a periodic waveform. So up here, a better way to represent this would be to call this 120 volts RMS to let all of the other engineers know that we are using an effective value for the periodic voltage that occurs between those 2 points and receptacle. Okay. So what we're going to do now is we're going to put this equation into action because I want to give you guys a couple of examples of it. And then we're going to tie things up with a neat little bow and look at a sinusoidal signal. So let's say that I have the following voltage waveform. So this is V of t. Here's t. And let's say that I have something that looks like this. Actually, let's make that 6 for scaling purposes. So this is our voltage waveform, and let's assume that it just repeats indefinitely. The period of this voltage waveform would be the amount of time it takes for the cycle to repeat itself, like so. And so let's give us some time indication here. So let's call this 2 seconds. Let's call this 5, 7, 7. So as a piecewise function, we could say that this voltage waveform is mathematically described as 3t volts from 0 is less than lowercase t is less than 2 seconds, and it looks like -2 volts for 2 seconds is less than t is less than 5 seconds. And then this repeats itself over and over and over again. Okay. The effective value of V of t could be determined by applying our effective value equation. 1 over t integral from 0 to t of v of t squared dt. And now we'll substitute in some relationships. So the first thing that we can do is we can observe that our period in this case is 5 seconds. Now, because I have a piecewise function, I'm going to break up my integral into 2 parts. I'm going to integrate from 0 seconds to 2 seconds. And I'm going to be integrating the value of our voltage waveform, 3t, and then I need to square it. And then I'm going to have the second part of my integration, where I'm integrating over the rest of our period. So this is going to be from 2 seconds to 5 seconds. My voltage waveform is simply -2 volts. And I square that. Like so. So I'm going to have 1 over 5 seconds goes here. The integral of 3t squared, so that's going to be the integral of 9t, 3t quantity squared is going to be the integral of 9t squared. The integral of 9t squared should be 9/3 t cubed. So I'm going to actually, well, yeah, 9/3 is 3 t cubed, evaluated at 2 seconds and 0 seconds. And then the integral of -2 volts squared, so 4 volts squared, dt is just going to be 4t. Evaluated at 5 seconds and 2 seconds. And so we're going to have 1 over 5 seconds. And so this is going to be 3 times t cubed. So 3 times 2 cubed minus 3 times 0 cubed. So that's my first bit. Plus 4 times 5 minus 4 times 2. That's my second part. And so this is going to look like 1 over 5 seconds times, let's see, 8 volts squared minus 0 volts squared plus 20 minus 8 is 12. And so that's going to look like the square root of 8 plus 12 is 20 volts squared second over 5 seconds. The seconds cancel each other out. Is going to look like the square root of 4 or 2 volts RMS. So effectively, this funny looking signal up here, where it's a triangle wave followed by a rectangular pulse repeating over and over and over again, delivers the exact same amount of average power to an arbitrary load as just a 2-volt DC source would, okay? So this is how we would apply our effective value equation for a piecewise function. Now let's look at something a little different. So a very commonly used signal in electrical circuits is the triangular wave, or the sawtooth wave, actually. Let's do sawtooth. So let's say that we have a wave that looks something like this. Just over and over and over again, this train of triangles. And let's say that the peak value of the triangle corresponds to some voltage V naught, and one period occurs in t seconds, so 2 periods occur in 2 t seconds, et cetera, et cetera, et cetera. One cycle of our voltage waveform looks like V naught over capital T. That's our slope. So that's the rise over the run multiplied by our variable lowercase t. Our effective value then is going to be the square root of 1 over the period times the integral over 1 period of V naught over capital T times T quantity squared dt. And let's look at what we've got here. So the slope squared is going to look like V naught squared over capital T squared. And it's a constant, so I can pull it out. So I'm going to have V naught squared over capital T squared for moving that slope of V naught over T, squaring it, and then moving it outside of my integration. And then I'm going to have the integral from 0 to T of T squared dt. I'm going to lump these terms together because I can. So that's going to look like V naught squared over T cubed. And the integral of T squared is just T cubed, but it will be evaluated at capital T or period and 0. Excuse me, 1/3 T cubed. And so what we're going to wind up having is V naught squared over 3T cubed multiplied by T cubed minus 0 cubed, where this bit right here cancels this bit right here. And so we wind up getting an effective value of V naught over the square root of 3. So the effective value of a triangular or a sawtooth wave only depends on the maximum amplitude of the triangular portion. As long as it's periodic and it's just repeating that sawtooth waveform over and over and over again, whatever the maximum value of the voltage is, We divide that by the square root of 3, and that is our effective value. Now let's look finally at a sinusoidal. So I'm going to depict it graphically just so we can look at the relationship between period and angular frequency again, because it's been a minute since we talked about that. And just for the sake of argument, let's say that our current waveform is measured in amps. So mathematically, I of t, sorry, let's make this IM, is given by IM cosine omega t plus some phase angle theta I, which in the way that I've depicted this circuit is, or excuse me, this signal is non-zero. Period of this signal is this distance t, this amount of time t. Go back to the triangular, the sawtooth wave thing, Sydney. Let me know when you're ready. Thank you. All right, so we have our sinusoidal current waveform, and we're investigating the relationship between capital T, the period, and the angular frequency. Now, we discussed this in our sinusoidal review lecture a while back. So effectively, we know that T is equal to 1 over the linear frequency, and we know that F, our linear frequency, is equal to omega over 2 pi. So that means we have omega over 2 pi is equal to 1 over t. And so t is simply 2 pi over omega. So our effective value equation, I effective, is going to be the square root of 1 over t, the integral from 0 to t of I squared t, which is going to look like 1 over t is omega over 2 pi times the integral from 0 to 2 pi over omega of 1/2 Im squared plus 1/2 Im squared, excuse me, cosine 2 omega t plus twice theta I dt. Much like I did yesterday, I can split this up into 2 integrals. And I'll have 1/2 Im squared dt here. And then 1/2 Im squared cosine twice omega t plus twice theta I dt here. Taking the square root of this whole thing. And so when I'm integrating my cosine twice omega t portion, the limits of my integration are telling me that I'm integrating over exactly 2 periods. As we discussed yesterday, when I take the integral of a sinusoid over any integer number of periods, the result is 0. Okay. So effectively, my cosine squared term is going to look something like this. And when I integrate it over the 2 periods, I drew it poorly, but effectively the area above the curve and the area below the curve should cancel out if I were able to draw correctly. And so we would get a 0 term here. And now what we're going to have is the square root of omega over 2 pi times a factor of 1/2 Im squared times the integral from 0 to 2 pi over omega dt. This bit right here just looks like 2 pi over omega minus 0 when we do the integration, which winds up canceling out that part there. And so we wind up getting Im over the square root of 2. Okay, so this is a very important result. I'm going to put a box around it. The magnitude of our current waveform divided by the square root of 2 is the effective value for our sinusoidal current waveform. Now I want you guys to realize something pretty neat here. The effective value is independent of our angular frequency, meaning that the value of omega does not matter, and our effective value is independent of our phase angle. So theta I literally does not matter. If we want the effective value of a sinusoidal signal, all we do is take the peak value of the sinusoid and divide it by the square root of 2 to get our result. Okay, we are going to put this into use here in just a couple of minutes, but you are asked a few homework problems where you have the effective value of a sum of sinusoids. And so I want to just talk to you very briefly about how you would do that. So this is kind of an aside just to get you through the annoying homework problems. So let's say that we have a signal V of t that is 8 volts plus 5 cosine 2t plus 10 degrees plus 13 cosine 5t plus, let's call it 20 degrees volts. And you wanted to find the effective value. Well, one extraordinarily long way to do it would be to literally multiply this function by itself, and we would wind up getting 7 terms once we made some simplifications. And then we would have to throw those 7 terms under our integral sign, do the integration, all that kind of stuff. It's a huge, huge pain in the butt. So instead, what I want to introduce is this equation. So if we ever have a signal that is comprised of the sum of sinusoidal signals, the effective value, V effective, is simply the square root of V effective for omega naught plus, squared, V effective for omega 1 squared plus V effective for omega 2 squared, etc. You may be asking yourself, how does this equation apply to this guy up here? So let me show you something a little tricky. 8 volts could be written as 8 cosine 0t plus 5 cosine 2t plus 10 degrees plus 13 cosine 5t plus 20 degrees. So we have, here's omega naught, here's omega 1, here's omega 2. So this signal actually is the sum of sinusoids, even though it has that DC term. Now, we do have to be a little bit careful though, because if we're trying to apply this equation, the effective value of a DC term is the DC term itself. So this is going to be 8 volts squared. The effective value of our omega 1 term is 5 over the square root of 2, because it's a sinusoid, and so we know the effective value of a sinusoid is just the magnitude of the sinusoid over square root of 2. And then we're going to have 13 over the square root of 2 squared as well. And then we can simply throw this into our calculator. So this is going to look like the square root of 64 plus 25 over 2 plus, let's see, 13 times 13, I think is 169 over 2. Comes out to be the square root of 161 for 12.689 volts RMS. So anyway, just wanted to show you how to do that very quickly, because you do have a homework problem or two related to that. And I don't know if it was the intention of the person who wrote the problem for you to do it out the long way, but I wanted to show you the short way because it's much less of a pain in the butt. All right, so going back to what we were talking about earlier, okay? So we know that the effective value of a sinusoidal function is just the magnitude of the sinusoid divided by the square root of 2. So early on in class yesterday, we learned that the average power absorbed by a generic network was given by 1/2 VM IM cosine theta v minus theta I. Well, we can play a little bit fast and loose here and say that Vm over the square root of 2 multiplied by Im over the square root of 2 times cosine theta v minus theta I must also equal the average power, since 1/2 is just 1 over the square root of 2 times 1 over the square root of 2. Well, Vm over the square root of 2 is the effective value for our voltage, and Im over the square root of 2 is the effective value for our current. And then we have cosine theta v minus theta I. And here's where I'm probably going to lose some of you, but it's okay. This is the real part of the following operation. V effective with an angle of theta v multiplied by I effective with an angle of theta I conjugate. This quantity here, the product of V effective angle theta v times I effective angle theta I conjugate, is what power engineers call the complex power absorbed by a network. And this is what we are going to spend the remainder of our class meeting talking about. It's complex power, okay? So the complex power is a quantity that's used by power engineers to succinctly characterize the power absorbed by a given load in a steady state sinusoidal system. It is a very powerful quantity, pun not intended, in steady state sinusoidal circuit analysis, because it contains all of the information pertaining to the power absorbed by a given load. So what I'm going to do really quickly here is recap a couple of things that we've talked about before, and then introduce a new domain for us to be working in, okay? So if we have a linear black box network, I'm sure you guys are tired of me talking about linear black box networks, but it'll be okay. And our linear black box network is sinusoidally excited. We can measure some voltage T across, or V of T across it, and some current I of T flowing through it, where V of T will be of the form Vm cosine omega T plus theta V, and I of T will be of the form Im cosine omega T plus theta I. These are our time domain representations of these signals, which I have absolutely beaten to death. So I'm going to move these down here. We're going to call this our time domain representation. I've learned that we can easily convert our time domain signals into the frequency domain by using phasors. where we would have a phasor voltage V is equal to Vm angle theta V, and we would have a phasor current I that is simply Im angle theta I, where this is our frequency domain representation. Well, when we're dealing with complex power, we typically work in what's called the RMS phasor domain. The RMS phasor domain is the exact same thing as the frequency domain, except that we use our effective values for our voltage and current. So I'm going to define an RMS phasor voltage as V with a squiggle over it. And this is simply our phasor voltage V divided by the square root of 2, because the effective value of a sinusoidal voltage is just the magnitude over the square root of 2, and our phase angle is going to remain unchanged. So this is going to look like Vm angle theta V over the square root of 2, which is the same as V effective angle theta V. We can do the same thing for our currents. All right, so our complex power, S, mathematically is simply the product of V RMS phasor times I RMS phasor conjugate. Complex power is the product of a voltage and a current. So dimensionally, we have units of volts times amps, which in the past we have referred to as watts. Now, there are multiple different parts of the complex power, and all of them are going to have dimensional units of volt times amps, but we give the different parts different units so that we can distinguish between them. So we are going to call the unit of complex power the volt ampere. Now, since our complex power is the product of the multiplication of complex numbers, it is going to be a complex number itself. We can represent this complex number either in polar form or rectangular form. So let's start with the rectangular form representation. So in rectangular form, this is going to look like V effective, I effective cosine theta V minus theta I plus J times V effective I effective sine theta V minus theta I. We call this bit right here the average power. And symbolically, we typically just call this P or P average. Average power has units of watts. Over here, we have what we're going to call the reactive power. Which we typically symbolize with the letter Q. And reactive power has units of volt amperes reactive, or VARs. Okay. So let's talk about what these two different parts of the complex power mean. The average power that we have here is literally the exact same average power that we've been dealing with for the last couple of days. It represents the portion of the complex power that is capable of doing work, okay? So effectively, it represents the portion of the complex power that resistors absorb, okay? Reactive power is the imaginary part of our complex power, and it represents what capacitors and inductors bring to the table, okay? So effectively, the reactive power is the portion of the complex power that constantly gets sent back and forth between our source and our load, since the average power absorbed by a capacitor or an inductor is zero. So reactive power is temporary energy storage for our system. Average power is the parts that just consume power, okay? Reactive power is critically important to keeping our electricity grid functional, because it is temporary energy storage. Without reactive power being injected into the system through capacitors and inductors, we would experience many more blackouts than what we currently do when loads are high at a utility. They also help maintain the rotation of rotating electric machinery like induction motors and things like that. So while this is power that's just getting sent back and forth between the source and the load, it is critical to its operation. Okay. We could also express the complex power in a polar form. I'll do that down here. So in polar form, this is going to be V effective, I effective, with an angle of theta V minus theta I. V effective times I effective is more commonly referred to as the apparent power, which I will give to you guys as the magnitude of S, our complex power, because that is literally exactly what it is. It's the magnitude of the complex number S. Apparent power is what power engineers design to. And so what I mean by that is the apparent power represents kind of a worst case scenario for a given system, because it doesn't take into account phase angles. So it's really kind of like the maximum value of the voltage multiplied by the maximum value of the current, without taking into account that there's going to be some cancellation of signals, okay? So if you've ever tried to buy a generator or an uninterruptible power supply for your computer or home appliance or anything like that, they are typically rated for some amount of average power, so like 1800 watts, and some amount of apparent power like 2100 volt amperes. Okay. As a power engineer, you use the quantity apparent power a lot to make sure that you're sizing your conductors properly, to make sure that you're not going to start fires and things like that. And then lastly over here, theta V minus theta I is more commonly known as the power factor angle. And we can represent this symbolically as theta S. Now, I understand that I have just given you a whole bunch of equations, and that can be annoying at best. So what I'm going to introduce to you now is a simple visual device that will help you learn and understand these relationships. And it's called the power triangle. So for a given load, we could plot the complex power on a complex plane where this is our real axis and this is our imaginary axis. So if our complex power S looks like this on our complex plane, the projection of S onto the real axis is our average power. The projection of S onto our imaginary axis is our reactive power. The length of this vector is our apparent power, and the angle formed with the real axis is our power factor angle. So succinctly, we can say that our complex power S is, by definition, RMS phasor voltage multiplied by the complex conjugate of our RMS phasor current. And in rectangular form, this looks like P average plus JQ. So average power plus J reactive power, or apparent power angle, power factor angle. The reason why I'm showing you this is because your calculators can give you either this rectangular form or this polar form. So effectively, if you can do this simple mathematical operation, it is literally just multiplying two complex numbers together, your calculator will give you average power and reactive power if you tell it to give you your answer in rectangular form, and it'll give you apparent power and power factor angle if you have it give you your answer in polar form. Okay? And we're going to work example problems here in a bit, maybe on Thursday, actually, since I've already talked for an hour at this point, to help reinforce these things. But really, all you need to know is how to do this operation that I've circled in red, and then use your calculator to figure out the rest. Okay. All right, so now I want to introduce some alternative relationships. For complex power. Okay, so in the RMS phasor domain, Ohm's law simply becomes RMS phasor voltage V is equal to RMS phasor current I times impedance Z. This should be pretty straightforward since RMS phasor voltage V is just phasor voltage V over the square root of 2, and RMS phasor current I is just phasor voltage I over the square root of 2. So effectively, we're just multiplying both sides of the equation by a factor of 1 over the square root of 2. Like this. Now, our complex power relationship is simply S is equal to V times I conjugate. Well, we can put these relationships together to figure out ways to calculate the complex power if we only know the voltage across our network of interest or only know the current flowing through our network of interest. Okay, so S is equal to V times I conjugate could be rewritten as V multiplied by V over Z conjugate. When I conjugate a fraction, I conjugate both the numerator and the denominator. So this is going to look like V conjugate times V over Z conjugate. I'm going to scroll down here real quick, and I'm going to refresh you guys' memory on what happens when I multiply a complex number by its complex conjugate. So if I have a complex number, A, that is equal to the magnitude of A, angle theta A, and I have a conjugate, this is just the magnitude of A, angle negative theta A. Well, when I multiply these two things together, this is just going to give me the magnitude of A times the magnitude of A with an angle of 0, because theta A plus negative theta A is equal to 0. So when I multiply a complex number by its complex conjugate, I simply get the magnitude of the complex number. So up here, that's just going to look like the effective value of the voltage squared divided by Z conjugate, meaning I don't even need to know the phase angle of the voltage in order to calculate the complex power absorbed by a particular impedance. If I just know the magnitude of the voltage drop across it as an effective value and the value of the impedance, that's all the information I need to know to calculate complex power. We can do a similar derivation for expressing things only in terms of our current. So S would be equal to V times I conjugate. V is simply I times Z multiplied by I conjugate. And so this looks like I conjugate times I times Z, or simply I effective squared times Z. using these relationships, we can actually see some interesting observations for resistors, capacitors, and inductors. So for a resistor, our complex power absorbed by our resistor is going to be simply the effective value of the voltage across the resistor squared divided by R, or the effective current flowing through the resistor squared multiplied by R. And from this, we can see that resistors absorb average power. For inductors, the complex power is going to be V effective over Z conjugate. So that would be V effective squared over omega L. And actually this would be over negative J omega L, because we're looking for the conjugate of the impedance, but a negative J in the denominator is the same thing as a positive J in the numerator. Expressed in terms of current, this is going to look like J omega L times I effective squared. And so we can say that inductors absorb reactive power. And finally, for a capacitor, sorry, this should be C. In terms of the voltage, we're going to have V effective squared divided by the impedance of the capacitor and the conjugate of that. Well, the impedance of a capacitor is 1 over J omega C, and the conjugate of the impedance of a capacitor is then 1 over negative J omega C. So we have V effective squared divided by 1 over negative J omega C, which makes our effective, which makes our complex power absorbed by a capacitor look like negative J omega C times V effective squared. And for, in terms of our current, we're going to have I effective squared over J omega C, and 1 over J looks like negative J in the numerator. From this, we can see that capacitors supply reactive power. And this is going to be a very critical thing to remember when we talk about power factor correction on Thursday's lecture. All right, so I have talked for 72 minutes straight. I do have several example problems that we could look at. Do you guys want me to work one of them today, or do you want to start off our lecture on Thursday with some example problems to solidify these relationships? One today. All righty, Ethan. So here is the first example problem that we are going to look at. The only one that we're going to do today, because I think I'm slowly killing you guys by talking so much. So we have a circuit, and it is already in the RMS phasor domain. And I can say that because the unit on our voltage is expressed in volts RMS. We are going to have some impedance ZA that I'm going to define in a moment. Here we have some impedance ZB, which I will also define shortly. Here we have some impedance ZC. And then here is a RMS phasor current source supplying 5 angle 45 degrees amps RMS of current. What I want us to find are the following things. Average power absorbed by impedance ZA, which reminds me I need to define these things. So let's say ZA is 10 plus J8. ZB is 12 minus J2. And ZC is 8 angle 30 degrees. The second thing we want to know is the apparent power absorbed by ZB. And lastly, let's find the reactive power absorbed by impedance ZC. So in order to solve for these three quantities, we need to know either the RMS phasor voltage across impedance ZA or the RMS phasor current flowing through ZA or both. To find the apparent power absorbed by ZB, we need the RMS phasor voltage across ZB, the RMS phasor current flowing through ZB, or both. And to find the reactive power absorbed by ZC, we need to know the RMS phasor voltage across ZC and the RMS phasor current flowing through ZC, or both. So where do you guys want to start? All right, since nobody is volunteering anything, I will start us off here. So we are going to find, we're going to do part C first. And the reason why we're going to do part C first is because IC is effectively already given to us, right? By inspection, we can see that IC is equal to negative 5 angle 45 degrees amps RMS, which is 5 angle negative 135 degrees amps RMS. From this, the complex power absorbed by element C, or impedance ZC, is the magnitude of the current flowing through C squared times ZC. So that's going to look like 5 amps RMS quantity squared times 8 angle 30 degrees ohms. And so let's see. That's going to be 200 angle 30 degrees volt amperes in polar form, or 173.205 plus J100 volt amperes in rectangular form. Since we want the reactive power, we only need to look at the imaginary portion of the complex power. So QC is simply 100 volt amperes reactive. So we're a third of the way done already. Now, let's solve part B next. So I'm going to figure out what the voltage VB is by using my modified nodal analysis technique. So effectively, I'm saying this node right here is ground, and this node right here gives me my RMS phasor voltage VB. So I will have VB minus 120 angle 0 degrees volts RMS divided by my impedance ZA, which was 10 plus J8 plus VB over my impedance ZB, which was 12 minus J3 minus 5 angle 45 degrees amps RMS is equal to 0. And I can solve this and find that VB is equal to 77.917 angle negative 0.238 degrees volts RMS. And knowing VB, I can say that the complex power absorbed by impedance ZB is the magnitude of VB squared divided by Z conjugate, which looks like 77.917 volts RMS squared over 12 plus J3 which comes out to be 490.813 angle negative 14.036 degrees volt amperes in polar form, or 476.158 minus J 119.040 volt amperes in rectangular form. since I'm trying to find the apparent power, I simply need to look at the magnitude. So this is the apparent power absorbed by impedance ZB, 490.813 volt amperes. It's 490.813 volt amperes. From here, I can find IA pretty easily. IA is just going to be 120 angle 0 degrees volts RMS minus VB all over ZA. So IA is 120 angle 0 degrees volts RMS minus VB over ZA. And if I substitute in my numbers, this is going to look like 3.286 with an angle of negative 38.219 degrees amps RMS. And from here, the complex power absorbed by ZA is just the magnitude of IA squared times ZA, or 3.286 amps RMS squared times 10 plus J8, which looks like 138.304 angle 38.660 degrees volt amperes in polar form, or 107.998 plus J 86.398 amperes. And because I'm looking for the average power, I simply need to take the real part, sorry, went slightly too far, of the rectangular form. So this is PA. 107.998 watts. All right, Ethan, you're the only person who toughed it out and let me do an example problem. So thank you for your diligence. Is there anything else I can help you with?